Hello everyone, this is Paul Hong Lin from National Taiwan University of Science and Technology. MOSFET stands for Metal Oxide Semiconductor Field Effect Transistor. Metal stands for the control. We use the metal control gate to control the current on the channel. The oxide stands for electric field. The control is controlled through the electric field. Therefore, there is no current flow through. Because there is no current flow through, you can save the energy to have the current flow through, I square R. There are three major components on the market today. One is MOSFET for switch and the CMOS. Second is for DRAM. One switch and one big capacitor. Third is the flash. It's MOSFET with another control gate called a floating gate. So there is a floating gate between the control gate and the channel in the flash memory. Now MOSFET, there are two major types. One is the P type, one is the N type. P stands for negative. The current flows through the channel is a positive electron. The current flows through the N type is the electron itself, stands for negative, N stands for negative. In the application, we always put the N type and the P type together right next to each other. So one control gate can control the N type and the P type at the same time. So in that case, we call it complementary metal oxide semiconductor, stands for CMOS. FIN-FET. Now in the old time, about year 2005, we find the planar FET doesn't work well. So we use the FIN-FET. FIN stands for fin, like the fin on a fish. We can have a better control over the gate. Like the fin on the fish, we can have a better control on the channel by the gate. Nanosheet FET, it comes from gate all around. Gate all around means the gate surrounding the channel. Lots of the sheet, so we can have more current go through. So that's called nanosheet FET. The main reason we do this is to enclose the channel by the gate totally surrounding as possible.
Hello everyone, this is Paul Hong Lin. Today we're going to talk about the MOSFET, Metal Oxide Semiconductor Field Effect Transistor. Now we have the different MOSFET in line here. So here the MOSFET, and I put them together, they become a CMOS. Now this is the fin, FIN-FET. Okay. Now if you put more than one fin together, then it's a multi-channel FIN-FET. This is the gate all around. So this is a multi-bridge FET. Now this one, if I put them together, this is the gate all around. And since I have more than one bridge, here, there will be the gate all around multi-bridge FET. Now this one is a fork gate all around FET, and the right hand side, this one is a CFET, complementary FET, field effect transistor. Now first, what is a transistor? I apply a voltage here, let's call it gate, then form the potential drop between here and here. Okay. The electric field is where the transparent block here. So gate, channel, transparent block. So field effect. The field form effect. The electric field in the transparent block form effect, which change the potential on the channel side. So then the electron can transfer from this called source and this called drain, can flow from source to drain. So what's a transistor? Apply electric field, control the current flow from source to drain, and that's called a transistor. The total name is field effect transistor. The field effect form the transistor effect by applying the voltage to change the current between the source and the drain. And that's called a field effect transistor. What's the MOS? The metal is here, normally called a gate. Oxide is where electric field form, which we don't conducting. The oxide part don't conducting current, but it form an electric field. So the oxide part actually block the current, but form the electric field, cause the effect, form the channel to allow the current from source to drain. Okay, so metal, oxide, semiconductor. Metal is a gate. Oxide is an electric field. Semiconductor is where the current flow. Metal, oxide, semiconductor. Now this is a negative channel. So negative, which is red, negative, which is red. The light blue will turn to red, which form a negative channel. When you apply positive voltage, then the electron will come from here to here. Now we come to complementary metal oxide semiconductor, CMOS. C stands for complementary. Okay. So the output will be here. And in this side, the complementary mean I have a positive, and the light red will become positive when apply a negative voltage here. Then I have a positive to positive connection. Okay. The complementary mean I put a gate together. I connect gate together. And I can connect the output together. Gate together and output together. So when you apply a positive voltage, the signal will come here, positive voltage, the negative channel, N channel will open. So signal will come here to do output. When you apply positive voltage, when you apply negative voltage, the P channel, P stands for positive, electron hole channel will open. So the current will come here through this light red, which is pink. Positive, the positive signal will come here, go to the output, which is in here. So the complementary mean, if I apply positive voltage, the signal will come from this side. If I apply negative voltage, the signal will come from this side to the output. Only one channel will be opened at one time, and at least one channel will be open. If you apply a positive voltage, here open. If negative voltage, here will open. So complementary mean only one will open and the signal will come out. The signal will come out from one of the input and go to the output here. But only one side will come out. One and only one side. Apply positive voltage here, apply negative voltage here. That's the word complementary. So next one is a FinFET, F-I-N-F-E-T. So FinFET means the channel itself look like the fin on the fish's back. And here is the source, here is the drain. And the control gate, source to drain. So here this whole thing, the blue thing, this part is the channel. And this substrate which don't carry any current. And it's also possible your fin use different material compared to your substrate here. The fin use different material with different color. Okay. Now when you try to control the gate, like this one, will wrapping the fin like this. Okay. Well, wrapping the fin like this one. So here's the fin, and the gate will be wrapping around them. Here's the gate. The gate, when you apply the voltage, in this case, since this is the red, so it's N channel, stand for negative. N channel, I apply the gate here, and they will change the voltage on this blue part, change it to the negative charge, allow the negative charge to go through. So negative goes through here and controlled by this gate. And the word of fin means that if you look from the side, it's just like a fish fin. The fish, here the fish, here the fish, and here's the fin.
If you have any question or comment about this course, you are welcome to contact me in the following line. Thank you for listening.
Okay, in this section, we're going to talk about gate-all-around. So what's gate-all-around mean? Now, here the source, here the drain, and here is the channel. Okay, and here's the gate. gate on the side, gate, metal oxide semiconductor, metal oxide semiconductor, gate, the electric field, and the channel. So gate on the side, okay. Then here, gate on top of the channel. So, and again, metal oxide semiconductor, gate on the top, okay. And the gate on the bottom as well. So gate, metal oxide semiconductor. So gate on the side, gate on the top, and gate on the bottom. So the gate on the top, on the side, on the bottom, totally surrounding the channel. So gate all on all around the channel. So that's gate all around. Now if I take the oxide part away, it's going to look like this. So that's the part where I take the oxide part away. You can see the gate totally surrounding the channel. Okay. Now the channel, if I take the top and bottom away, you can see it look like a bridge between the source and the drain. And another thing is it look like a sheet, S-H-E-E-T. It look like a bridge, B-R-I-D-G, and it look like a sheet, S-H-E-E-T. So sometimes we call it a bridge. Okay, now this is one bridge or one sheet. So sometimes one bridge is not enough. Why? Because to have the gate all around effect, the size of the bridge cannot be very large. The effect of the gate must be able to affect the whole channel, the whole plate, the whole sheet. So there's a limit to the size of this channel or this bridge or this plate. So to have enough current, limited size means limited current. To have enough current, we need more than one bridge. Then it becomes multi-bridge. Okay, so one bridge, two bridges, three bridge. So I take it apart, you can see. And here's the source or the drain, and here's the source and the drain, and here's the bridge. One bridge, two bridge, three bridge. So I take a slice down, and here's the gate. If I look around each of the bridge, or each of the fleet, or each of the channel, the bridge totally all around this bridge with the oxide layer in between. Again, if I look at this bridge, the gate, the yellow part, totally all around the bridge or the channel here in blue. So metal oxide semiconductor, metal oxide semiconductor, metal oxide semiconductor. And there are totally three bridges. I slice it down so you can see totally there are three bridges in this place, and all connecting between the source and the drain. Now notice one thing. This is a gate, right? The yellow part is gate. Source and the drain. There is a oxide layer, an insulating layer between the gate and the source or drain, because the current is not allowed to flow between the source or drain to the gate. So the oxide layer in between. And the channel, of course, source, channel surrounding by the gate, channel surrounding by the gate, channel surrounding by the gate, then the channel surrounding by the oxide without a gate, then to the drain. So in this case, we can see the three bridges between the source and the drain. There are three bridges. There are three bridges connecting between the source. Okay, wait a second. There are three bridges connecting, 1, 2, 3 bridges connecting between the source and the drain. Okay, now that's what it looks like the gate all around. If I slice in different direction, okay. So the gate from top plate affect the channel through this outside layer, and source and the drain and the bridge. So here, compared to this one, you can see the bridge 1, bridge 2, bridge 3 between the source and the drain. So if I slice a different direction, and that's what it look like. So here, gate, outside, bridge 1, bridge 2, bridge 1, 2, 3, bridge, 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 then the outside there, then the gate again. So if I look at the gate, the channel here, the channel actually have a gate top on the bottom, gate on the part, this channel, gate on the top on the bottom, this channel, gate on the top on the bottom, and again the gate on the top of all the 3 plate, then the gate on the bottom, top and the bottom as well. So it's a 3 bridge gate, or it's a 3 bridge, 3 fleet gate all around. Sometimes 1 bridge is not enough. You need to more than 1 bridge. And in their design, you can have a 2 bridge design, 3 bridge design, or 1 bridge design. Now we come to the complementary gate all around. So this is the N type because the red color stands for negative, blue color stands for positive. Source and drain, then the blue one will turn to red when apply the positive voltage. You go around, the current will go through. So, and then it's covered with the gate and gate. Okay, so here is the channel, gate all around it. The same way we can do for positive channel. So positive, positive, and when you apply negative voltage, the current will go through. The current will go through from positive source to positive drain. As well, I have a gate here, gate on the bottom, and gate on top. So that's the gate all around for the P channel. P stands for positive. Now, if I connect the 2 gates together, just like I do the complementary metal oxide semiconductor, then how will I do? So that's the N channel, that's the P channel. Let's put them together. Okay, and I put the top, and I put the bottom, and put the top. Okay, now you might notice it's gate all around for the N channel and gate all around for P channel. At the same time, the gate itself is connected together for both the P type and N type. Now, if we apply the positive voltage, then the N channel will open, P channel will close. If you apply the negative voltage, then the P channel will open, N channel will close. So only one channel will open at one time, and one and only one channel will open. So this is a complementary stand for. So I put them together, then they become a complementary. It's a complementary, and it's a gate all around for both N type and P type. So that's complementary gate all around. Now there are 3 ways to do the complementary gate all around. The first one is, okay, now let's come to complementary multi-sheet metal oxide semiconductor. Now multi-sheet, that's what the multi-sheet look like. So you have more than 1 sheet or more than 1 channel on the same blocks. Now that's a complementary stand for. The P channel, this is a P channel, the N channel. P channel and N channel all share the same gate. So I put them together. That's the complementary. That's the complementary multi-sheet. So you can see I have 1 sheet here, and 2nd sheet here. and they are complementary because they share a gate. They share a gate. This one better. They share a gate. Okay, put it apart. They share a gate. The gate affects the N channel. Put them together. Put them side by side. You can see. Okay. The gate share the gate, the P channel and the N channel all share the same gate. Okay. And I have more than one sheet. So that's I have more than one sheet. Put them, stack them together to get an up. Okay. So that become the. So here's one sheet, and I stack it up. Second sheet. Okay. So one sheet down here. You can see the pink here. One sheet down here. Second sheet down here. You stack it up. Then they become the multi-sheet complementary metal oxide semiconductor. Okay, one sheet, two sheet. You can have three sheet. And what's this one? Well, when you make this, the sheet itself made from the silicon base down here. So that's what's the level for silicon. Then the silicon will become, then the part that's not connecting, because now the channel will be filled up back with the oxide layer in the blue one, like this one. Okay, so that's the multi-sheet complementary metal oxide semiconductor. Now next one is a fork sheet complementary metal oxide semiconductor. Now the word fork comes from here. So when we look at here, so it's metal oxide semiconductor, but inside here, this one is totally insulated layer. Compared to here, so between the P channel and the N channel, they have oxide gate and oxide. So I have a oxide gate oxide, totally three different material, and between the source N channel and P channel, N channel and P channel. So, but we want to reduce the size between them. So what I do, I use one insulating layer to replace the insulator, gate, insulator, 3 layer. Then I can shrink the different distance between the P channel and the N channel. Okay. Another thing is, since I separated the N channel and P channel, so I can use different material, different metal material. Note here, the purple material and the pink material are different metal with different work function. Now, different work function can allow the gate to control the channel better for different P channel and N channel. Okay. So I use the word fork is in here. I have multi-sheet, right? So here, so it's like here, and 1, 2, 3. So this is like a fork. If I look here, it's like a 1 finger, 2 finger, 3 finger, and fork this side and fork this side. So the fork sheet metal oxide semiconductor. So because it look like fork, 1, 2, 3. So and 1, 2, 3. Look at fork on both sides. And the only one outside layer between the N channel, sorry, the P channel and the N channel here. Okay. Now finally come to the CFET, complementary field effect transistor. Now this is all complementary, right? I mean the gate apply voltage both to the P channel and the N channel. Okay. Yeah, P channel and N channel. But in this case, the P channel and N channel are right next to each other. So if you look from the top of the chip, the P channel here, N channel here, and they actually have different chip space. Okay. So if you want to save the space, make more transistor on the same chip. The way we do it, we stack it up. We put a P channel atop the, we put the P channel atop the N channel. Okay. tilted. Okay, I'll put a P channel atop the N channel. Now the N channel has higher conductivity. Now because all the connection come from top, so you allow the P channel, N channel down here with higher conductivity. Here, so the connector from this here, and N channel has longer conductivity loop. P channel has smaller. That way they can be a similar current for different conducting loop. However, if one bridge is not enough, CFET allow the more sheet, 1 sheet, 2 sheet, 1 sheet, 2 sheet, okay, or even 3 sheet to stack up together. Now you might notice one thing: the color around the N channel are different from P channel. So this one, the pink color and the purple color, actually stand for different metal with different work function. They are all metal, but they have a different work function. So when you apply high voltage to allow the N channel to flow through, or low voltage to allow the P channel to flow through, they have a better control on the gate to the channel. Now, the C channel, here again, the C channel stands for you stack up one, normally the P channel atop the N channel, and that's the CFET stand for. Of course, this is the base and this is the semiconductor where you do it up. And when you make the block up, you fill up the material which you don't need with the oxide to insulate between the channel and the substrate.
If you have any question or comment about this course, you are welcome to contact me in the following line. Thank you for listening.